This section concerns electromagnetic theory, which is a combination of electrical forces and phenomena, magnetic forces and phenomena, and as was discovered by Maxwell in the mid-1800s, this actually includes also electromagnetic theory, which includes, of course, light or electromagnetic radiation. The section that we're beginning now is the section on electricity, and this chapter is on electrical forces. Now, there are certain fundamental terms that we have for electrical charge, conductors, and insulators that most of you are familiar with from your earlier days in school. We're all familiar with static electricity and lightning and different sources of electrical charge. For example, electrical attraction that comes from things like styrofoam or hair when we brush our hair. And we're familiar, of course, with the fact that where electricity comes from, somewhat in general. But we can ask the question, what is electrical charge? And the answer to that is that no one really knows what electrical charge is. It's a property of some of the fundamental particles, electrons, protons, and neutrons, and the things that that are composed of those particles, which is all of ordinary matter. And some of these particles, like the electron and the proton, have electrical charge, and some do not, like the neutron and certain other particles. So it's kind of an intrinsic property of matter, kind of like mass. And we know that electrical charges are positive and negative, and that like charges, like positive and negative will repel, while the opposite charges, plus and minus, attract one another. Kind of a little bit different from gravity, where everything is positive in gravity, all mass is positive, and forces are attracted between positive mass and positive mass. It's the opposite sign for electrical forces. And most of you are also familiar with the fact that Benjamin Franklin, who lived from 1706 to 1790, was the first one to actually define electrical charge and link it to lightning. And you're familiar with his famous kite experiment. We know that charges have certain properties. The first of all, the charges are quantized. By quantized, we mean that we might write down here charge. Charges are quantized. And by quantized, we mean that they occur only in certain integer multiples of a fundamental amount. And this is the charge on the electron, or the basic charge. The basic charge is often called E, and it's as a symbol for the electron, and it's 1.6 approximately times 10 to the minus 19th coulombs, where coulomb is the unit of the electrical charge. Millikan proved this in 1909 and actually measured the charge on the electron. This is how we measure charge in terms of units of coulombs of charge. Okay, so it's quantized. That means you can have 1 of this amount, 2 of this amount, any integer times that amount. So in general, charge can be any integer, positive or negative or 0, times this electronic charge here. The only exception that's ever been discovered associated with this are the quarks. And the quarks can have 1/3 of this charge and 2/3 of this charge. But if we take 1/3 of this and use the same integer, then it turns out still that all charges are basic multiples of that basic amount of charge. As you know, conductors allow charge to flow freely, and other materials where it can't flow as freely are called insulators. Insulators are things like glass, wood, materials that do not have free electrons in them. Most of your conductors that allow charge to flow freely are things like metals, especially things like copper and silver. Those are the best conductors, but all of the metals allow some charge to flow relatively easily. And that's because if you think about the atom and the way the atom is composed, you have a nucleus and then you have electrons that go around the outside. If we have an unfilled shell, like maybe there are 2 electrons in an outermost shell, and this shell may be filled and the shell inside that is filled, then atoms tend to want to have their outer shells complete. And since this is not complete, these two are not bound as tightly. So it's very easy to knock one of these electrons off and move it to an adjacent atom, and that's what constitutes the flow of electrical current. We can also induce electrical charge. Now, how is electrical charge induced? Well, if we take an object here, let's imagine this is now a metal, this might be iron or something like that, and we bring a positive charge up near it on the end of a stick or something like that. We bring this nearby, this repels the positive charge here, so the positive charge will all go to the far side of this object, leaving this side negatively charged. And this is, of course, we have polarized this into positive charge on this side, negative on this, by virtue of this positive charge here. If we were to take this part and connect it by a wire to the ground, and this is the symbol for the ground, connecting it to the earth, then this positive charge would jump off of here because it's trying to get away from this positive charge here, and it would leave the object here negatively charged overall. Then when we remove this charge, it would leave it overall with a negative charge on it. This is called charging by induction. And you can see we do that with a negative charge. One of the most important things about charges are linear superposition. By the linear superposition, we're referring to the electrical forces, which we'll talk about in the next section. And these electrical forces, like from one charge, let's imagine we have a positive charge here, another charge here, let's just call this Q1, we'll call this Q2, and have another one Q3. Each of these will exert a force on a charge Q here. These might be repulsive forces pushing on it, this might be an attractive. If I add up these force vectors, the total force on this charge is always the linear vector sum of these charges. And this linear superposition property is incredibly important in physics. It means that if we understand the fundamental forces, we can understand complex forces. This does not occur in the social sciences, where in fact we do not have linear superposition. You can know what happens in one circumstance with one person, know what happens with another person, and then you put both of those people together in that same circumstance, and you have an entirely different circumstance, entirely different effects on the people, because their interaction overwhelms the separate interaction that you might have. So this gives you an overall effect of what charges are like. They're measured in coulombs, they're conserved. That means if I look at the total amount of charge in an enclosed area, and I add it up, the positives and the negatives, whatever that total charge is, it will not change unless it flows out or flows in. This is similar to the conservation of energy and the conservation of mass, conservation of linear momentum and angular momentum, which we've already discussed. And so we have a conservation of this charge. That means that charge can neither be created nor destroyed. So what are the salient points here? Charges come from electrons, protons, and fundamental particles, an excess of one or another. We don't really know what charge is. They're positive and negative, and they can be in any integer amounts times the basic charge. We know it's measured in units of coulombs of charge. It's conserved. Conductors and insulators allow and do not allow charge to flow, and we can have charging by induction. One of the most important concepts is this of linear superposition. Linear superposition allows us to do complex things from simple things.